Hello again, and welcome to Echoes of the Forgotten Earth, a place where the biggest questions don't crash through the ceiling. They settle softly, like dust in a beam of morning light. Wherever you are, whatever hour it is in your slice of this spinning world, I'm glad you found your way here. Maybe you're listening with sleepy eyes or with a mind that won't quite turn off. Maybe you're under a blanket that still remembers your day or tucked into the soft corner of a couch. Maybe night has gone wide and quiet, or the sun is just climbing over rooftops, turning windows into pale squares of gold. However you arrived the way most of us do, carried by the ordinary miracle of breath, heartbeat, and gravity doing what they've always done. And wherever you are, you share something with everyone else listening, and with every creature under the same sky, every moth tapping a porch light, every owl threading the dark, every coyote pausing before it crosses a road. We are all living on a planet balancing almost delicately on the conditions that make life possible. It's easy to forget how rare that is. Earth feels steady, predictable. There's comfort in routines, seasons arriving more or less on schedule, rain showing up often enough, a moon that waxes and wanes with quiet patience. We plan as if stability is a promise. We build houses, argue about parking, book flights, and imagine next year as if the ground under our lives will keep behaving like ground. But sometimes, usually when the day finally lowers its voice, another thought slips in. Could that ever change? Not a cinematic ending, not the sky splitting open. Something subtler, a shift that starts small enough to dismiss and then becomes the new background. A few systems strained here, a few failures there. The invisible agreements we have with air, water, and soil beginning to loosen. Could we ever end up looking back at a planet we once called home from somewhere else? Before we try to answer, hold that question like a stone found on a beach. Turn it slowly. Feel its weight. Not to scare yourself, not to spiral, but to name what you're really asking. We're not talking about one city struggling for a decade, or a storm knocking out power for 3 days. We're asking about habitability at its deepest level. Breathable air, drinkable water, temperatures bodies can survive without constant mechanical help. We're asking whether the baseline life's basic requirements could become unreliable on a global scale. And it helps to remember, Earth has not always been gentle to creatures like us. For most of its 4.5 billion year history, it wasn't a place for human lungs or skin. Life has existed here for nearly 3.8 billion years, but for a long stretch, life meant microbial persistence organisms thriving in chemistry we'd call hostile, in oceans and vents, without oxygen, without eyes, without any need for what we consider normal. Humans are different. We are, bluntly, particular. We need a narrow temperature range, atmospheric pressure that keeps water liquid and blood where it belongs, a stable rhythm of seasons, fertile land that can hold roots, an ozone layer that filters the sun's sharper edges, and fresh water we can access without crossing a continent. That very specific comfort has been reliably in place for only a thin slice of time. Even within that slice, Earth has never been entirely calm. Ice ages rolled in and retreated. Seas swallowed coastlines and stepped back again. Species vanished, sometimes quietly, sometimes in waves that reshaped the living world. Ecosystems disappeared when change arrived faster than they could adapt or outrun. So what's unusual about now is not that climate shifts. Earth is a planet of change. What's unusual is the speed and the fingerprint. So many changes are happening rapidly, and in many cases, because of us. That human part returns again and again in this story. Because asking whether Earth could become uninhabitable is another way of asking whether we'll push a living system beyond its ability to recover. Whether what we build, burn, bury, and extract is nudging the planet's balancing act into a stagger. But we're getting ahead of ourselves. For now, step back with me. If Earth is home, what makes it a home in the first place? What are the ingredients, the physical, chemical, and biological factors that let this particular rock in space carry bodies like ours? Start with distance. Earth sits in the so-called Goldilocks zone. Not too hot, not too cold, far enough from the sun for water to exist as liquid much of the time. That sounds simple until you realize the window is narrow. Shift Earth. A few million kilometers closer, and the long math changes. Water cycles distort, temperatures climb, the slow loss of oceans becomes imaginable. Move it farther out, and the planet struggles to hold warmth. Global freezing becomes less fairy tale, more plausible chapter. We are, literally, in a lucky orbit. Then the atmosphere. Not just that Earth has one, but the recipe. Mostly nitrogen, a large portion oxygen, and a thin but powerful trace of carbon dioxide and other gases. That balance didn't arrive as a gift. It took billions of years, and the work of tiny photosynthetic organisms exhaling oxygen into a world that wasn't ready for it. Even now, the margin is thin. Change oxygen a few percentage points, and human physiology breaks. Alter pressure enough and liquid water becomes unstable. Without the right air pressing gently on us from all sides, blood would boil at room temperature. It's obscene in its bluntness, and true. Gravity helps hold that air in place, keeping the atmosphere from drifting into space like a slow sigh. And when people say casually, "We'll just move to another planet," gravity is one of the first quiet obstacles. Most worlds can't hold an atmosphere like ours, or they hold the wrong gases, or they orbit stars that flare too often, too violently. And then there's the magnetic field, another protector that rarely gets thanked. Earth's liquid iron core generates a magnetic shield that deflects solar wind and cosmic rays. Without it, the atmosphere erodes over time, and radiation reaches deeper. Life becomes a harder bargain. The field has weakened and flipped before. It recovered, but recovery takes thousands of years. It's strong, not immortal. Water is part of the bargain too, not only having it, but having it in all three states. Ice, liquid, vapor, circulating through oceans and clouds and rivers and snowfields. That diversity drives weather, builds seasons, and runs the world's quiet machinery. But water can slip out of balance. Melt too much ice and seas rise into streets. Evaporate too much and deserts widen. Fresh water is finite where we need it. Aquifers can be drained faster than they refill. Rivers can be diverted, poisoned, or overdrawn. A planet can have plenty of water and still be deadly if the water lives in the wrong places. And finally, biodiversity. The living network that keeps so much else stable. Trees drawing carbon from the air, insects pollinating crops, bacteria fixing nitrogen, reefs buffering coasts. 1,000 quiet relationships that behave like biological insurance. But networks can fray. Pull out enough threads and the cloth doesn't hold. So when we ask whether Earth could become uninhabitable, we're really asking, how many systems would have to fail? And how likely is it that we'll push them there? It's rarely one dramatic event. More often it's a gradual tipping. Changes stacking until certain places can no longer support human life, cities too hot without constant cooling. Rivers running dry after years of drought. Coastlines slipping under rising water. Storms destroying infrastructure faster than it can be rebuilt. Habitability doesn't always vanish like a light switching off. Sometimes it becomes patchy, uneven. Some regions remain livable for a while. Others become marginal. Migration grows, resources strain, tension builds, and the planet itself, the rock, the orbit, the spinning, will still be here. That's the strange part. Earth isn't at risk of disappearing. What's at risk is Earth as a home. The conditions that support our lives, our agriculture, our cities, our assumptions about weather and water and shelter. Some scientists talk about planetary boundaries, thresholds that, if crossed, could push the Earth system into a less stable, more unpredictable state. Climate change, biodiversity loss, ocean chemistry, land transformation. We've already crossed several, or we're close enough to feel the heat of the edge. But instability is not inevitability. Systems can recover. Some thresholds are reversible. others aren't. The real question isn't only whether Earth can remain habitable, it's whether we are willing and able to keep it that way. So I want to linger here a moment longer, in the feeling of how tuned this place is. Because once you understand how narrow the window is, the rest of the story snaps into focus. Earth, for all its beauty and endurance, isn't an unbreakable fortress. It's more like a well-made instrument, strong, yes, but sensitive. Capable of carrying life across millennia, but not immune to wear. And if we really let that settle into the bones, then will Earth become uninhabitable? Starts to sound less like a curse and more like an invitation. Because what happens next is not entirely out of our hands. If you've ever watched sunrise spill gold along a landscape, or stood outside on a mild evening while a soft breeze wandered through trees, you felt it. That quiet sense of rightness. This place fits us in a way that can feel almost intentional. It didn't have to be this way. The universe offers countless arrangements of temperature, light, chemistry, and gravity that would have made Earth sterile. The version we inhabit is one outcome fortunate, and it begins, as so many stories do, with an ordinary star and a planet placed just so, where water stays liquid and life becomes complicated. So take a breath if you can, slow and easy. You're participating in one of Earth's oldest exchanges, and in the space between that breath and the next, there's still time to choose what kind of world we're helping build. If you're still here, we'll keep walking. Our star isn't rare. If you like labels, it's a G-type main sequence sun steady enough that life can plan around it. That steadiness is a kind of mercy, but even mercy has parameters. We orbit about 93 million miles out, and our path is close to circular. That mildness matters. It keeps the yearly swing in sunlight from turning into a constant shove between scorch and deep freeze. Then there's the tilt about 23.5 degrees, which gives us seasons that are pronounced enough to move water and life around, but not so extreme that large parts of the planet are repeatedly punished. And the moon, so often treated as decoration, is also a stabilizer. It helps keep Earth's tilt from wandering chaotically over a long time. Without it, the climate would likely swing harder, and normal would be harder for ecosystems to hold on to. The moon also pulls on the oceans, creating tides that shape coasts and estuaries, nurseries for life and buffers for storms. Repeating rhythms matter, they always have. The atmosphere is another rhythm made physical. It's not only what fills your lungs. It filters sunlight, holds enough heat to keep oceans liquid, and burns up many incoming rocks before they reach the ground. Its composition is a delicate recipe. Enough oxygen for animals, enough greenhouse gases to prevent a frozen world, not so much that the blanket becomes smothering, and carbon dioxide tiny in percentage, huge in effect, acts like a lever. Add more and the planet holds more heat. Warmer air holds more water vapor, which traps more heat. Ice retreats, dark surfaces absorb more sunlight, and the system amplifies itself. None of this is ideology, it's physics. For a very long time, human civilization lived inside a narrow CO2 band, the range in which agriculture and large, stable societies became possible. Then we opened an old vault, coal, oil, gas. Carbon stored for millions of years returned to the air in a few generations. The numbers rose fast enough to be visible in a single lifetime, and the climate began to respond in ways that matched the chemistry. Water, too, is part of the agreement. Not just having oceans, but having water in 3 states at once. Ice, liquid, vapor circulating through clouds, rivers, snowpack, and groundwater. That cycle feeds forests, fills reservoirs, and shapes weather. Yet water is unevenly distributed, and modern life leans hard on storage and diversion. When drought stretches or snow melts early, the system feels it immediately. Agriculture strains, cities ration, ecosystems thin. Beneath all of it is soil alive when it's healthy, brittle when it's not. Fertile soil is a living structure of minerals, microbes, fungi, air, and moisture. It holds water like a sponge, feeds roots, and stores carbon. Degrade it through overtilling, erosion, deforestation, and you weaken the land's ability to handle both flood and drought. It's one of Earth's quiet feedback loops. Damaged soil releases carbon and loses resilience, which makes climate shocks hit harder, which damages soil further. And then there's biodiversity, the living web that keeps the whole thing forgiving. Pollinators, microbes, forests, wetlands, reefs, they're not scenery. They're stability. They buffer shocks, recycle nutrients, and keep air and water within ranges we can live inside. When that web thins, life doesn't necessarily vanish, but it becomes less reliable, less redundant, more brittle. A planet can still be habitable on paper, and yet feel like a constant emergency in practice. So the danger isn't usually one clean apocalypse. It's a gradual narrowing, some regions becoming too hot to work outdoors for parts of the year, coastlines facing chronic flooding, fire seasons stretching longer, water becoming unreliable, food systems wobbling under heat and extremes. The rock remains. The home conditions fray. That's why Uninhabitable is often a map, not a switch. Some places stay comfortable. Some become expensive to defend. Some become seasonally dangerous. Some are quietly abandoned, not in one dramatic moment, but because rebuilding stops making sense, insurance disappears, wells turn brackish, and disasters arrive faster than recovery. And still, the most important line in this entire story is simple. Instability is not inevitability. Earth's systems can recover when pressure drops. Air can clear when combustion falls. Forests can regrow. Fisheries can rebound. Cities can redesign for heat and flood. The window hasn't closed yet, but it doesn't stay open by accident. So we keep going, not to chase fear, but to sharpen the picture. Because once you see how many layers make home possible, you also see the leverage points, where human choices can protect those layers or peel them back. Next comes the part that feels invisible until it isn't. The sky as a system. Most of what makes Earth comfortable happens in a thin layer near the ground, the troposphere. It's shallow enough that a commercial jet can cross it, yet it holds almost all weather, most breathable air, and the moving chemistry our bodies depend on. Above it sits the stratosphere, where ozone absorbs much of the sun's harsh ultraviolet. Higher still, the atmosphere thins towards space. We live at the bottom of a shell. That shell has been stable enough for civilization, but it's not fixed. It is shaped by biology and geology, and now by industry. Oxygen feels permanent because it's everywhere, but it was made. Photosynthetic organisms reshaped Earth by releasing it. That change enabled complex life, but it also shows a truth we tend to forget. Atmospheres can be transformed. Today's transformation is faster. Carbon dioxide is only a trace gas, yet it works like a thermostat lever. It traps heat. So does methane, which is rarer but more potent in the short term. So does nitrous oxide, long-lived and powerful. These gases exist naturally, but we're adding them quickly by burning fossil fuels, changing land, and running agriculture at scale. The planet responds the way physics says it will. More heat stays in the system. Warmer air holds more moisture. Oceans absorb most of the excess heat and a large share of the CO2, which slows atmospheric warming but comes with costs. Sea level rise from thermal expansion and ocean acidification as dissolved CO2 shifts seawater chemistry. On land, warming and drying can increase fire risk. Fires release stored carbon and damage forests that used to absorb it. This is why climate change isn't just a bit warmer. It's a reshaping of patterns. More intense heat waves, heavier downpours in many places, longer droughts in others, and a higher baseline that turns old extremes into common events. It's also timing spring arriving earlier, snow melting sooner, ecosystems falling out of sync. And then there's the air people actually breathe. Unbreathable doesn't usually mean oxygen disappearing. It more often means air becoming harmful. Fine particulate pollution, ground-level ozone, industrial emissions, and increasingly, wildfire smoke. Smoke can travel far, turning regions nowhere near flames into health hazard zones. Heat can worsen ozone, dust can rise more often where land dries and vegetation thins. Indoors, tighter buildings can trap pollutants if ventilation is poor. Air quality is where climate stops being abstract. It becomes a daily decision. Open the window or not, let kids play outside or not, take the run or wait. And like most burdens, it lands unevenly, often hardest on communities already closer to highways, industry, and weaker healthcare. Still, air is also where we have proof that change works. When emissions fall, air improves. Regulations have cleaned skies in many places. Cleaner power and cleaner transport don't just reduce warming, they reduce the daily harm of breathing. The atmosphere responds faster than many people think. So the question sharpens again. Not, will the planet have air? But will the air stay safe enough, often enough for ordinary life? From here, we move to Earth's slow memory ice. Because ice doesn't just reflect sunlight and raise seas when it melts. It also stores the past in layers like a library you can drill into. And in those layers you can see both Earth's ancient rhythms and the abruptness of the signal we're adding now. Ice looks like the opposite of life cold, still, almost outside time. But it moves. It records. It answers questions the atmosphere can't keep for long. When scientists want to know what Earth was like before thermometers and satellites, they drill ice cores. Layer by layer, snow compacted into ice holds tiny bubbles of ancient air, traces of dust and ash, and isotope signatures that reveal past temperatures. The deeper you drill, the farther back you go, hundreds of thousands of years. In Antarctica, more than 800,000 years of climate history can be read like pages pressed flat. The story those pages tell is steady in one way and unsettling in another. They show natural swings between ice ages and warmer interglacials, paced by slow orbital rhythms and amplified by feedbacks. And they show carbon dioxide and temperature rising and falling together, sometimes one leading, sometimes the other, but always linked. Then comes the rupture. In the last century and a half, CO2 rises beyond the natural range seen in those records, and it rises fast. Not over millennia, but over generations. The speed matters because big systems have inertia. They don't respond like a light switch. They respond like a ship, slow to turn, then hard to stop. Mountain glaciers are retreating across the world. Alps, Andes, Himalayas, Alaska, Rockies. It's not only a loss of scenery. Glaciers store water and release it gradually, supporting rivers during dry seasons. As glaciers shrink, river flow can spike briefly, then decline as the reservoir runs down. For millions of people, that turns reliable into uncertain. At the poles, the scale widens. Greenland holds enough ice to raise global sea level by about 7 meters if it melted completely. Antarctica holds far more. Full melt is not a near-term scenario, but the direction is clear. Both are losing mass. And the mechanisms aren't just surface melt. Warmer oceans can thin ice shelves from below. Those shelves act like braces, slowing the glaciers behind them. Lose the brace, and ice can accelerate into the sea. This is where the word tipping point becomes more than a metaphor. Some ice systems may have thresholds beyond which retreat becomes self-sustaining, driven by the shape of the land beneath the ice, and the way grounding lines migrate. Scientists debate details and timelines, but the risk is real enough to matter. Certain losses could be difficult to reverse even if warming slows later. Ice also controls sunlight. Bright ice reflects energy back to space. Dark ocean absorbs it. As Arctic sea ice declines, the region warms faster. An albedo feedback that helps explain why the Arctic is heating far more rapidly than the global average. The polar changes don't stay polar. They influence sea level everywhere and can affect broader circulation patterns. Then there's permafrost frozen ground that holds enormous stores of carbon. As it thaws, microbes wake up and release CO2 and methane. The land can slump and collapse, damaging infrastructure and altering ecosystems. Permafrost emissions are a feedback. Warming can unlock more warming. Ice teaches a hard lesson about momentum. Even if emissions fall, some sea level rise is already committed because oceans store heat and greenhouse gases persist. That doesn't make action pointless. It makes it decisive. How far the system goes depends on how much more we add before we slow down. From ice, the story moves into the places most humans live now, cities. Because climate change doesn't just alter landscapes, it tests infrastructure, power grids, housing, and public health. Cities can amplify risk through heat and flooding. But they can also concentrate solutions fast if we choose to build them that way. Cities can feel like proof we've stepped outside nature concrete. Glass, lights that never go out, water arriving through pipes as if it was summoned. But cities are inside the same atmosphere, under the same sun, dependent on the same water cycle. Climate change doesn't stop at the city limits, it concentrates there. The first urban signal is heat. Cities create their own warmth through the urban heat island effect. Dark roofs and asphalt absorb sunlight and release it slowly at night. Buildings trap heat in street canyons. Trees and soil natural cooling through shade and evaporation are replaced by pavement. Add waste heat from vehicles and air conditioners, and a heat wave becomes sharper and more dangerous. The danger isn't only the daytime peak, it's the night. When nights stay hot, bodies don't recover. Heat stress accumulates, and the risk rises fastest for the elderly, the very young, outdoor workers, and anyone without reliable cooling. Heat can be a quiet killer. Not dramatic, just relentless. And it's not distributed evenly. Wealthier neighborhoods tend to have more trees, parks, better insulation, and more access to air conditioning. Poorer neighborhoods are more likely to be dominated by highways, industry, and older buildings that trap heat. So the same heat wave becomes different realities inside the same city. Climate change doesn't create inequality, but it often intensifies it. Cities also face water problems at both extremes. Heavier downpours can overwhelm stormwater systems built for an older climate. Streets become rivers, sewers back up, subways and tunnels flood. Coastal cities face storm surge on top of rising seas, so flooding becomes not just a rare disaster, but a recurring condition. Meanwhile, drought can strain reservoirs and rivers supplying metro regions, turning water into a planning crisis instead of a background utility. Then there's the grid. Urban life depends on electricity for almost everything. Pumping water, refrigeration, hospitals, communications, banking, transit, cooling. During heat waves, demand spikes. If the grid fails, consequences cascade. No elevators, limited water pressure, spoiled food, overheated apartments, disrupted medical care. Reliability becomes a public health issue. There are also pressures we don't always label climate, but that shape habitability in cities: noise and light. Constant noise affects sleep, stress, and cardiovascular health, and it pushes wildlife away or forces it to adapt. Artificial light at night erases darkness, disrupting human circadian rhythms and confusing birds, insects, and sea turtles. These changes are subtle, but they alter the living texture of a place. Yet cities are also where solutions can scale fastest. Cool roofs and reflective pavement reduce heat. Trees and green corridors lower temperatures and improve air quality. Green roofs absorb rain and reduce flooding. Permeable surfaces let water soak in instead of rushing into drains. Building codes can require passive survivability structures that stay safer during outages. Transit, walkable streets, and dense housing can reduce per-person emissions. Microgrids and distributed solar can improve resilience. Floodplains can be restored. Wetlands can be rebuilt. Some areas can be redesigned around water instead of fighting it. But adaptation isn't only engineering. It's governance. It's fairness. Who gets protected first? Who gets relocated? Who can afford insurance? Who has access to cooling centers and clean air during smoke events? Poorly designed adaptation can deepen inequality. Good adaptation reduces it. And even the best adaptation has limits. Some places can't be defended indefinitely at reasonable cost. That's where managed retreat plan supported relocation enters the conversation. It's painful, political, and often unavoidable if chronic risk keeps growing. Unplanned retreat is worse. It abandons the poorest first, leaving others trapped until the next disaster forces the decision. So the urban story returns us to a simple point. Habitability is not only physics, it's systems. And systems fail, not all at once. but in chains. From here, we move back to the air specifically, what it means for air to become unbreathable in practice. Not oxygen disappearing, but pollution, smoke and heat turning ordinary breathing into a recurring risk. We don't think about air until it hurts. A strange smell, a tight chest, a sky turned amber by smoke, a child's cough that becomes normal. Air feels infinite because it's everywhere, but it's also a condition, and conditions can degrade. When people picture an unbreathable Earth, they often imagine oxygen vanishing or the atmosphere turning instantly toxic. That's not the realistic path. Oxygen levels aren't dropping at anything like a rate that would threaten near-term breathing. The more likely danger is quieter, air that still contains oxygen but carries enough pollutants to damage bodies over time or to make certain days and seasons unsafe to be outside. This is already true in many places. The main culprits are familiar and brutal: fine particulate matter, PM 2.5, nitrogen dioxide, sulfur dioxide, volatile organic compounds, and ground-level ozone. PM 2.5 is especially dangerous because it's small enough to reach deep into the lungs and enter the bloodstream, raising risks of heart disease, stroke, respiratory illness, and premature death. And it doesn't land evenly. Pollution follows highways, refineries, ports, power plants, often near communities with less money and less political protection. In those neighborhoods, environmental problems become healthcare problems, school problems, work problems. The air becomes inequality you can inhale. Now add wildfire smoke. As heat rises and landscapes dry, many regions are seeing longer, more intense fire seasons. Smoke travels hundreds or thousands of miles, turning distant cities into hazard zones. And wildfire smoke isn't just wood smoke anymore. Fires increasingly burn through homes and industrial materials, releasing plastics, paints, treated lumber, and chemicals. The mix can be especially harmful for children, older adults, pregnant people, and anyone with heart or lung conditions. Heat makes air worse in another way. Ozone. High up, ozone protects life from ultraviolet radiation. Near the ground, it's a pollutant formed when sunlight reacts with vehicle and industrial emissions. Hotter weather accelerates ozone formation, so heat waves can arrive paired with ozone spikes, exactly when lungs are already stressed. In arid regions, drought and land degradation can also expand dust storms. Fine dust reduces visibility and harms lungs. It can carry spores and microbes long distances. Air becomes a highway not only for gases but for particles and biology. And then there's indoor air, the air most people breathe most of the time. Cooking smoke from wood or charcoal remains a major health risk in many parts of the world. Tighter, energy-efficient buildings can trap pollutants without good ventilation. Mold rises after floods. Radon seeps into basements. A safe shelter can become a container for harmful air if it's sealed without clean exchange. So could Earth's air become unbreathable in the dramatic sense oxygen collapse? Not anytime soon by any mainstream scientific expectation. But could large regions become effectively unlivable at times due to smoke, ozone, heat, and chronic pollution? That's not hypothetical. It's happening. And here's the important counterweight. Air is one of the systems where we know policy and technology can work. When emissions fall, air quality improves. Cleaner power, electrified transport, better transit, and efficient buildings reduce both greenhouse gases and the daily harm of pollution. Sensors and satellites make pollution harder to hide. The atmosphere responds faster than many people think. Air, in other words, is leverage. But air is only one boundary. Even if we cleaned it perfectly, humans and ecosystems still face limits, especially heat and water. So next we move to the edges of adaptation. What bodies can tolerate, what ecosystems can track, and what habitable really means when the safe zone starts to shrink. Life is tougher than it looks, just not in the ways that help us most. Microbes can thrive in boiling springs, acidic pools, deep rock, and the dark ocean around hydrothermal vents. Some organisms survive drying almost completely and return when water comes back. Life in general is inventive. So if you ask, Could Earth become uninhabitable? The answer depends on for whom. For microbes, Earth is hard to truly sterilize. You'd need a planet-scale catastrophe, runaway greenhouse conditions like Venus, or an event that strips the atmosphere and oceans. That's not the near-term risk we face from human activity. For humans, and the complex ecosystems we rely on, the question is sharper because our habitability isn't just, can a few survive? It's whether ordinary life can function. Food systems, water systems, shelter, health, and stability. The first hard limit is the body. Humans shed heat by sweating, and sweating only works if it can evaporate. In high humidity, the air can't accept much more water vapor, and the cooling mechanism fails. This is why wet bulb temperature matters. It combines heat and humidity into a measure that maps onto survivability. Around a wet bulb of 35 degrees Celsius, 95 degrees Celsius, prolonged exposure can be fatal, even for a healthy person resting in shade with water. Below that threshold, risk still rises sharply, especially for outdoor workers, the elderly, and anyone without cooling. As warming continues, some regions are already approaching these physiological edges more often. That doesn't mean whole countries suddenly empty out. It means more days when outdoor labor becomes dangerous, cooling becomes essential infrastructure, grids are stressed, and power failures become deadly. Heat is only one boundary. Water is another. Food is another. Disease is another. And ecosystems face parallel limits. Species generally have three options as climates shift. 1. Move to track suitable conditions. 2. Adapt biologically or behaviorally. 3. Die out locally or entirely. Movement sounds easy until you remember the modern world is fragmented. Habitats are split by roads, farms, cities, fences, and dams. A species may need to move north or upslope, but the corridor is blocked, and sometimes the destination doesn't exist. Mountaintop species face the cruelest geometry. As temperatures rise, they climb until the mountain ends. Adaptation also has a speed limit. Evolution takes generations. Fast reproducing organisms can shift quickly. Slow-growing trees and large mammals often cannot. If climate zones move faster than forests can migrate, you get stressed ecosystems, pest outbreaks, drought vulnerability, and more fire. Then comes mismatch. Ecosystems depend on timing. Flowers and pollinators, plankton blooms and fish larvae, predators and prey. Climate shifts timing unevenly. A plant blooms earlier. Its pollinator doesn't emerge earlier because its trigger is day length, not temperature. The relationship weakens. Those small failures ripple upward. These aren't always cinematic collapses, they're quiet unthreadings. At extremes, droughts, floods, heat waves, and recovery time disappears. Systems can survive shocks if they can recover. When shocks arrive too often, the system stays in repair mode until it breaks. Disease dynamics shift too. Warmer temperatures expand some mosquito and tick ranges. Changes in rainfall create new breeding habitats. Heat can stress wildlife and weaken immunity. Displacement after disasters increases crowding and sanitation stress. Meanwhile, oceans keep changing, warming, acidifying, losing, oxygen-pushing marine life to cooler waters and threatening reefs and fisheries that support hundreds of millions of people. So what does uninhabitable look like in the real world? Not a single on-off switch. It looks like gradients. Regions that remain productive, though more extreme. Regions that become marginal, still inhabited but costly and stressful. Regions that become seasonally dangerous. Smoke, heat, floods that interrupt normal life. Places that become quietly abandoned after repeated loss, failing insurance, unreliable water, or endless rebuilding. This is already visible in small ways. Communities hit repeatedly by wildfires or floods, farms shifting crops or failing, heat making outdoor work unsafe at certain hours. It's important to be precise. Earth is not about to become Venus. But we are pushing parts of the planet toward conditions incompatible with how we currently live, especially where infrastructure and governance are weak, and for people with the fewest resources. And because humans move, the pressures spread. Migration increases, often within countries. Cities swell faster than planning can handle. Competition for water and housing intensifies. Politics hardens. Climate becomes a stress multiplier. Rarely the sole cause of instability, often the force that widens existing cracks. Still, resilience is real. Nature rebounds when pressure is reduced. Forests regrow if protected. Fisheries recover when managed well. Air improves when combustion drops. Soil rebuilds when treated as living. Humans can adapt through design, policy, technology, and cooperation if we choose to. Which leads to the next question. If the livable zone is narrowing in some places, can we widen it again? That's where we go next, into response. Mitigation and adaptation. What works, what scales, and what actually reduces suffering. If you zoom out far enough, it can feel like a trap. Warming air, rising seas, fires and floods, thinning biodiversity systems under stress. It starts to sound like inevitability. But the climate system isn't fate. It's physics plus choices. That means the future isn't one track. It's a range of outcomes shaped by how quickly we cut emissions, how well we adapt, and how fairly we protect people who are most exposed. There are two categories of response, and we need both. Mitigation, reduce the drivers of climate change, mainly greenhouse gas emissions and strengthen sinks, forests, soils, wetlands. Adaptation, reduce harm from the climate change already here and from what's locked in by inertia. Mitigation without adaptation leaves people exposed in the near term. Adaptation without mitigation becomes an endless escalation. Higher seawalls, bigger pumps, more air conditioning, while the hazard keeps growing. Mitigation, bending the curve. The core problem is simple. We're adding greenhouse gases faster than Earth can absorb them. So mitigation is stopping that addition. Electricity is the big lever because decarbonizing power lets us decarbonize other sectors. Clean generation solar, wind, hydro, where appropriate, geothermal, nuclear in some regions, combined with modern grids and storage cuts, emissions and enables electrification. But it's not just build renewables. It also means expanding transmission to move power where it's needed, improving grid flexibility, storage, demand response, interconnection, retiring coal, and reducing reliance on unabated gas. Designing for reliability during heat waves and storms, efficiency is the quiet powerhouse. Insulation, heat pumps, efficient motors, LEDs, industrial upgrades. It's often the fastest, cheapest way to cut emissions because you stop wasting energy in the first place. Transportation is technology plus design. Electric cars help, but so do transit, walkable streets, safe cycling, and rail because reducing car dependence reduces energy demand altogether. Aviation and shipping are harder. Options include efficiency, operational changes, and alternative fuels, with honest accounting about scale. Industry needs targeted fixes, electrified heat where possible, low-carbon cement and steel pathways, material efficiency, use less, recycling, and circular manufacturing. Carbon capture can play a role in truly hard-to-abate processes, but it can't be a license to keep emitting everywhere. Agriculture and land matter hugely. Stop deforestation, restore ecosystems, build soil carbon, reduce fertilizer emissions, cut methane where possible, and reduce food waste. Methane reductions are especially valuable because they can slow warming relatively quickly. None of this requires a single miracle invention. It requires deployment, maintenance, and governance coordination at scale. Adaptation, living through what's already here. Even with rapid mitigation, CO2 lingers and oceans store heat, so impacts continue for decades. Adaptation is making life safer in the climate we now inhabit. Common adaptation themes: heat, tree canopy and shade, cool roofs, passive survivability in buildings, heat warning systems, cooling centers, worker protections, healthcare readiness, floods and storms, upgraded drainage, restored floodplains and wetlands, zoning that avoids repeat losses, elevating critical infrastructure, coastal defenses that mix engineering with living systems, drought and water, reuse and recycling, leak reduction, smarter irrigation and crops, watershed restoration, governance for shared basins, fire, defensible space, fire-resistant codes, early detection, fuel management where appropriate, and limiting expansion into high-risk corridors, health, smoke filtration, disease surveillance as vectors shift, emergency plans built for compound disasters. Because compound risk is the new normal. Heat plus blackout, fire followed by flood, hurricanes stacked on sea level rise. Adaptation has to plan for cascades, not single events. The hard truth, not everywhere can be defended. Some areas will become too expensive or too risky to protect indefinitely. That's where managed retreat planned, funded relocation becomes the humane option. Unmanaged retreat is worse. It pushes the poorest out first and leaves others trapped until the next disaster. Justice isn't optional. Climate risk is uneven, and so is capacity to respond. Good adaptation isn't only engineering, it's equitable access to cooling and clean air, worker protections, public health investment, fair insurance and disaster support, and real participation in decisions. And a just transition matters for mitigation too. If people lose livelihoods without alternatives, backlash follows. If benefits are shared cleaner air, cheaper energy, stable jobs policy becomes durable. Why the window is still open. Climate change isn't binary. Every fraction of a degree matters. Every avoided ton of CO2 matters. Every year earlier matters. Less warming means fewer extreme heat days, less long-term sea level rise, lower risk of irreversible ice loss, less strain on food and water, and fewer ecosystems pushed past thresholds. And that returns us to the question people reach for when they feel cornered. If Earth becomes too hard, can we leave? Next, we measure the escape to Mars narrative, what it would actually take, and why repairing Earth is far more achievable than replacing it. When people feel cornered, they look for exits. In the climate conversation, one exit keeps reappearing: Mars, the Moon, space habitats. The emotional shape is the same. If Earth becomes harder to live on, we'll build somewhere else. It's an understandable instinct. It's also a dangerous one, if it becomes a substitute for protecting the only planet we already know can support billions without constant mechanical life support. What Earth gives us for free, Earth provides continuously. Breathable air at the right pressure, abundant liquid water, radiation shielding from a thick atmosphere and magnetic field, gravity. Our bodies evolved for soils and ecosystems that grow food using sunlight, temperatures that in many places don't require sealed suits, a biosphere that cycles nutrients and decomposes waste. We complain about weather, but Earth's baseline is astonishingly kind. Mars isn't a backup. Earth-Mars offers none of that as a default. It has an extremely thin atmosphere, mostly CO2, far too low pressure for unprotected humans, no breathable oxygen, higher surface radiation due to weak shielding, extreme cold and big temperature swings, pervasive dust that degrades machinery and solar power, water mostly locked as ice, toxic perchlorates in much of the regolith, low gravity, switched 38% of Earth, with unknown long-term effects on health and reproduction. A human on Mars survives only inside an engineered bubble. That bubble must provide pressure, oxygen, heat, water recycling, food production, and radiation protection, and it must be reliable. A small failure isn't an inconvenience. It can be fatal. On Earth, a storm can mean discomfort and disruption. On Mars, an extended power failure can end a settlement. Terraforming, not a climate plan. Terraforming. Mars, thickening its atmosphere, warming it, creating stable surface water, is not a near-term tool. It runs into hard constraints, available gases, energy, timescales, and would take far longer than the decades in which Earth's climate risks are unfolding. Terraforming is an interesting thought experiment. It is not an emergency exit. Even success wouldn't solve the Earth problem. Let's imagine an extraordinary achievement, a permanent Mars base that grows. Dozens become hundreds, hundreds become thousands, maybe more over centuries. It still leaves billions on Earth. Climate change isn't asking whether a small number of humans can survive somewhere else. It's asking whether billions can live decent lives here, where food systems, water systems, coastlines, and cities already exist. There's also a moral hazard. If escape feels plausible, urgency softens. Fantasy becomes permission to delay. Repair versus planetary construction. Keeping Earth habitable is repair. Stop adding heat-trapping gases. Restore ecosystems. Adapt infrastructure. Making Mars habitable is planetary construction. Create and maintain the conditions Earth already supplies. Repair is hard. Planetary construction is beyond hard. Space still matters, just not as an exit. Space exploration helps Earth more than it replaces it. Satellites track storms, drought, fires, ice loss, sea level, deforestation. Planetary science teaches us climate dynamics, Venus as runaway greenhouse, Mars as atmospheric loss. Asteroid detection and deflection improves planetary defense. Technology spin-offs support monitoring and resilience. Looking outward can sharpen our understanding of what makes Earth rare, and that brings us to the final turn. Not as a wish, not as a threat, but as a thought experiment that clarifies dependence. What happens if humans don't solve it? If we vanish? Or simply stop? Next, a world without us. What rebounds quickly? What scars last? And what habitability means when the dominant species is gone? Imagine for a moment that humans simply stop. Not a cinematic last day, no single catastrophe with sirens and fire in the streets. Just absence. Cities empty. Power plants unattended. Cargo ships drifting nowhere. The constant human pressure extraction. Combustion. Noise ending like a long-held breath released. What happens to Earth then? The first truth is blunt and clarifying. Earth does not need us. We need Earth. Days to weeks, lights out, air clears fast without operators and maintenance, power grids fail. Cities that never slept go dark. Water treatment plants stop. So some places see short-term contamination. But air quality improves quickly as vehicles and industry stop emitting. The loudness of the human world traffic, machinery drops away, and the planet's own sounds return. Rivers constrained by pumps and diversion begin to shift back toward their natural rhythms. In many watersheds without constant industrial discharge and fertilizer runoff, water systems start trending toward recovery unevenly, but noticeably. Nature doesn't take over overnight, but it begins. Months to years. Plants reclaim edges. Wildlife returns without mowing. Herbicides and clearing. Vegetation re-enters first through margins. Cracks in pavement, rail corridors, empty lots, medians. Vines climb fences. Saplings appear where you don't expect them, because seeds were always waiting for a chance. Animals follow opportunity. Urban wildlife expands. Foxes, coyotes, boar, deer, birds nesting in quiet buildings. In some regions, larger mammals reclaim corridors that highways once cut. With hunting pressure gone, predator-prey systems begin to rebalance. The pattern is consistent. Remove disturbance, and life fills space. Decades. Cities decay into habitat. Buildings are constant effort disguised as permanence. Within decades, roofs fail from water damage. Steel rusts. Concrete cracks. Subways flood. Bridges weaken. Coastal cities rot faster as saltwater accelerates corrosion and sea levels, still rising from climate momentum push inland. This isn't clean rewilding. Toxins remain, heavy metals, asbestos, chemical residues. Some hotspots stay dangerous for a long time, but across many regions, ecological recovery outpaces structural decay. Plants stabilize soils, wetlands reform in low areas, birds diversify, insects rebound where pesticides are gone. the world becomes less human-shaped and more ecologically textured. Centuries, the long unwind of our emissions. If humans vanish tomorrow, the greenhouse gases already emitted wouldn't vanish with us. CO2 remains elevated for a long time, slowly absorbed by oceans and land. Warming continues for a while because the system has inertia, and sea level keeps rising for centuries as oceans expand and ice responds. But without ongoing emissions, CO2 gradually declines. Forests spread in many regions. Soil carbon can rebuild. Wetlands store carbon again. The planet moves toward a new equilibrium, not necessarily the climate humans knew, but one Earth can sustain. Earth has recovery mechanisms. They aren't fast, but they are real. What scars remain? Some human impacts are long memory, extinctions, permanent on human timescales. The web can regrow, but not with the same threads. Plastics fragment into microplastics rather than truly disappearing, persisting in soils and sediments. Persistent toxins, heavy metals and long-lived pollutants linger, cycling or burying slowly. Nuclear waste, localized, long-term hazards as containment eventually degrades without management. So the dominant story isn't pure ruin. It's reorganization. The humbling conclusion. Making Earth truly uninhabitable for life is extraordinarily difficult. Making it significantly less habitable for humans is much easier, and we're already doing parts of it. The stakes were never planet dies versus planet lives. The stakes are how much suffering occurs, how much stability we preserve, how many ecosystems remain intact, whether billions can live ordinary lives without constant emergency Earth will persist. The question is whether we choose a future where Earth remains a wide, forgiving home or a narrower one where safety depends on machines, money, and luck. And the most important fact, after everything, we still have agency. Agency doesn't mean control. It means influence. It means we can still decide whether uninhabitable becomes a headline word or just a warning we took seriously in time. And the way that decision shows up won't be grand and cinematic. It will look like thousands of choices that add up. What we power, what we build, what we protect, what we stop pretending is normal. Because home isn't a feeling. It's a set of conditions. Breathable air, drinkable water, temperatures the body can tolerate, soils that can grow food, oceans that still function as climate buffers rather than becoming a cascade of losses, a living web thick enough to absorb shocks. The risk we've been circling is not that Earth vanishes, it's that Earth becomes less forgiving, patchy, expensive, and dangerous in more places, more often. A world where habitability exists, but only behind barriers. Air filtration, constant cooling, imported water, fortified coastlines, rebuilt roads, rebuilt again. A world where the ordinary becomes an engineering project. And when that happens, the question, will Earth become uninhabitable, changes shape. It becomes two questions. For whom? Where? Because a warmer, more volatile Earth doesn't distribute hardship evenly. It follows wealth, infrastructure, and power. If we do nothing, the future is not one shared fate. It's a widening gap, protected enclaves and exposed margins. That's the part we can still choose not to normalize. So what does choosing look like? In plain terms, it looks like stopping the easiest emissions first. Leaks, waste, inefficient buildings, dirty power that has cleaner replacements. It looks like building clean electricity and the wires to move it, because nothing else scales without power. It looks like treating cities as climate infrastructure, shade, cooling, drainage, transit, passive survivability. It looks like protecting and restoring what already stabilizes Earth for free: forests, wetlands, reefs, soils. It looks like preparing for compound disasters, not single ones, because that's how the real world hits. It looks like telling the truth about retreat where retreat is safer, and funding it so it isn't just abandonment with paperwork. It looks like justice being a design requirement, not a paragraph at the end, because systems break fastest where people are already stretched thin. And it looks like time being treated as what it is, the most valuable resource in the story, because every year of delay locks in more heat, more sea level rise, more ecological strain. And every fraction of a degree avoided buys breathing room, literally, in some regions. It buys fewer days that cross physiological limits, fewer fires that turn air to poison, less salt in groundwater, more reefs that survive another summer, more forests that remain carbon sinks instead of becoming fuel. The planet doesn't ask for perfection, it responds to direction. If emissions fall, warming slows. If pressure on ecosystems drops, recovery begins. If we stop tearing holes in the net can hold. So here is the question that replaces fear with clarity. Not, will Earth become uninhabitable, but how habitable do we choose to keep it? Because the window is still open narrow, but open. And if you take nothing else from this opening chapter, take this. Earth is not an unbreakable fortress. It's a well-made instrument. Strong, yes, but sensitive. And the music it plays, stable seasons, predictable rain, breathable air, abundant life, depends on how we treat it. So take a breath, slow and easy. You're inside the system you're trying to understand. You're part of the exchange that has been running for billions of years. Carbon and oxygen, water and heat, life and air. And the next step in this story is not deep time or cosmic distance. It's the present tense. The specific things shifting right now, in the air above you, the oceans beyond your horizon, the soil under your feet. That's where we go next.